All right, so we're going to look at a section. This one kind of sometimes to a lot of people feels like it's out of place. It almost, I mean, it is technically a thermochemistry topic, but the reason why it's in this chapter is because it's related to breaking bonds, and it's looking at specifically how bonds break. So this deals with specifically, okay, how much energy is it taking me to break bonds, or how much energy do I have to put in? So one thing that seems real simple, but you have to know, and it's for some reason people have a hard time with it, is it takes energy to break bonds. You have an electrochemical attraction between elements, and what you're doing is you're removing that. So you're removing a stabilizing force. So for you to break something, you put energy in. Just like if I have 20 Legos put together, you have to exert a force to break those Legos apart. Obviously not ridiculously a lot for that, but you do have to exert a force. So whenever you break a bond, it will be positive, and you need to make sure you understand that. And just what you always wanted, there's one more way to figure out enthalpy, and the way you do this is you actually do your bonds. So what you do is the easiest way I think is you break all your bonds, and again this is the summation symbol for math, so you sum up breaking all your reactant bonds, and then you subtract that from the summation of all your product bonds. And what you're doing is you're breaking all the bonds you're starting with, and then you're subtracting all the ones you're making. On the next slide, there's average bond enthalpies. They would be given to you on the test and on your AP test, and in college and stuff. You don't have to memorize what a carbon single bond is. If your delta H is negative, you're exothermic, which means you're releasing energy to the system. To the surroundings. And if your delta H is positive, then you are endothermic, and you are absorbing energy from the surroundings. So just remember, if you're exothermic, what that means is product bonds are producing more energy than it took to break the reactant bonds. And obviously, if you're endothermic, reactant bonds took more energy to break than the product bonds produce when they form. So you want to have kind of an idea of what in the world that means, so that you can kind of help it. So what we'll do is I'll show you the next slide where it has like the different bonds and stuff, and then we'll do an example, and then you'll be good. So this is an example. On your test and on your AP test, they don't give you all of these. This is just from your book, and you can see like they've actually calculated, if I break a carbon and a hydrogen bond, what is it? And that's different than if I break a carbon to carbon bond. And a carbon to carbon bond is different than if I break a carbon to carbon double bond. So you just have to find all these guys and make sure you know what they look like, because that's going to dictate what you're breaking. So here's the one we're going to do. We have methane reacting with chlorine gas for making a chloromethane, and some hydrochloric, I guess it's hydrogen chloride gas. So I'm just going to draw them out quick. I'll pause it and then come back so you can see the pictures, so we don't waste that much time. But you kind of keep in mind, you need to know what these guys look like so you can figure out what's breaking and what's not. Alright, so what I did was I just drew the actual pictures out. So I drew methane, I drew chlorine gas, and you're welcome to do this. You can do this in your head, you can do it whenever you get a chance. So depending, you might want to draw these out, you might want to do these in your head. I'm going to break all the bonds and make all the bonds, because that's the only way that I can be sure that I'm not going to make any mistakes. But if you want to, you can very easily see you can only do the ones that actually change and only do the ones that actually are different. So like you can see here, on both sides, carbon has 3 hydrogen bonds. So realistically, you don't have to break them and you don't have to make those, because they don't change. I do it just because I don't want to worry about missing a bond. But if you're a risk taker, you feel free to try where you only do the ones that actually change. And again, that's your choice. So what I'm going to do is I'm just going to show you what I'm actually going to plug in, and then we'll put the numbers in. So what you see here is the formula for the delta H, and what I did is I did all the bonds for the reactants, minus all the bonds for the product. So what I did first is I looked at my methane, and I saw that there were 4 of these carbon to hydrogens. So I said, okay, I have 4 of those, and then I also have 1 single chlorine to chlorine. Then I put those in a bracket. I did the product side, and I said, okay, over here I have 3 carbon to hydrogens, 1 carbon to chlorine, and 1 hydrogen to chlorine. So once you know what you're doing, then you just need to look up the numbers. So I'll plug in the numbers. You can try it on your own and just make sure you get the right answer. So all I did here is I went to my chart and I found how much energy does it take to break a carbon to hydrogen bond, and I plugged it in. How much does it take to break a chlorine to chlorine bond? Plugged it in. And then make sure you're very careful with this negative sign, because it does have to distribute through all of these. And what you should get is at the end you get a negative 104 kilojoules per mole of reaction. And this indicates it's an exothermic reaction. So the bonds that are being formed release more energy than the amount of energy that had to be put in to break the bonds for this one.